Thank you. Thank you for the introduction and a kind invitation for giving me this opportunity to speak. So I want to talk about geometric and arithmetic theta correspondences. So let me give you an overview of what they are. So we have heard from Witek's talk about the classical theta correspondence. So I'm going to start with a dual pair. So typically a symplectic group, SPW and OV, an orthogonal group. Or you could take a skew Hermitian space, take its unitary group, and another Hermitian space V and its unitary group. So what the classical theta correspondence does, roughly speaking, is giving a way to lift automorphic forms from one of the group G to the other group H. So what are geometric and arithmetic theta correspondence? So roughly speaking, for example, the geometric theta correspondence, which was initiated by Coulthard-Nielsen in the 80s, is to give you a correspondence, a way to lift the automorphic forms on one group G to cohomology classes on a Shimura variety associated to the other group H. Okay, and the arithmetic theta correspondence, which is often referred to as Coulthard's program, who initiated in the 90s, is going to give you a way to lift automorphic forms on G to algebraic cycles, okay, on the corresponding Shimura variety associated to G to H. Okay, so these theories from this table, you can see they are kind of variants or generalization of the classical theta correspondence, interesting in their own right. But also, like the classical theta correspondence, has very important applications. Okay, since we are in the summer school about long-length program, so the classical theta correspondence has important applications to establish explicit long-length functoriality, for example, from classical groups to GLN. Okay, and I'm going to mention, for example, the geometric theta correspondence also have application to study the cohomology of Shimura varieties, and people use these tools to establish Hodge conjecture and Tate conjecture, okay, for certain Shimura varieties. And the arithmetic theta correspondence give you a way to understand algebraic cycles on Shimura varieties, and they also have important applications to BSD conjecture, and it's higher dimensional generalization known as the Beilinson block conjecture. Okay, I hope I'm going to give you some idea how these applications play out at the end. Okay, so today I'm going to use the example of unitary dual pairs as an example to discuss all these properties. Okay, so let me begin with unitary dual pair to set up some notation and review a little bit what Witek discussed in his lecture. Okay, so I'm going to start with a quadratic extension of number fields F over F0, and W will be a standard split skew Hermitian space of dimension 2n. Okay, and G will always denote its unitary group, which is a quasi-split unitary group over the base field. Okay, so the other group is associated to Hermitian space of rank M, okay, over this quadratic extension, and H will always denote its unitary group. Okay, and also some notation. There's a standard Ziegel parabolic subgroup inside G, which I denote by P, whose levy is denoted by M, and unipotent radical is denoted by N. Okay, they are very explicit in this case. Okay, so attached to this pair, we have the Weil representation. So here's a bit of review. Okay, so A will denote the ring of Adels. Okay, so here's a bunch of auxiliary data. I'm going to denote eta, the quadratic character associated to this quadratic extension. And I fix a character chi, which is the character of the Adels of F, such that it extends eta to the n, okay, on the Adels of F0. Okay, whatever this character is, it's used to split the metapletic cover, as discussed in Witek's lecture. Okay, and by choosing this chi and picking an additive character, we can prove, we can pull back the distinguish the representation of the metapelic group to get a representation of G times H. Okay, so that's the Weyl representation, which I denote by omega. Okay, and in fact, it has very explicit realization on the space of Schwarz functions, n copies of identic points of V. Okay, so I think at some point Wittek was trying to tell you that the formula are very explicit, but he didn't have time, but I have slides, so I will just show you. Okay, so indeed, Wittek didn't lie to you, it's very explicit. Okay, you can determine the action on the Levy nilpotent element. Okay, this Weyl element and the element in H very explicitly in these formulas. Okay, so you can see this is explicitly given by some character value and determinant. It's given by adding the character of the trace of the moment matrix given by the tuple vectors. And this Weyl element gives you a very important incarnation of the Fourier transform. Okay, so in the Weyl representation, we can start to do the classical theta lifting. Okay, so associated to a Schwarz function phi, we can define the two-variable theta function by just summing over the rational points and use the Weyl representation to act on it. Okay, so you can use this explicit formula of Weyl representation to check that the theta function is in fact automorphic. Okay, in other words, it's invariant under the rational points of G times H. Okay, and the most important thing is to check its the action under the Weyl element and its consequence of Poisson summation formula. Okay, and the key thing in theta lifting is to use this two-variable theta function as the integral kernel. Okay, to lift automorphic forms on one group to the other group. Okay, so let me remind you, if I have a cuspidal automorphic form on G, I can define theta lift, okay, to be simply the Petersen inner product of this two-variable theta function and function on G, the automorphic form on G. Okay, and the result, the theta lift, it now becomes an automorphic form on the other group, H. Okay, and if I start with a pi, a cuspidal automorphic representation of G, okay, I can look at all the Schwarz functions and all the automorphic form in pi, and I look at this equivariant linear map simply given by associating the corresponding theta lift. Okay, and the global theta lift, theta v of pi, which is sub-representation of the automorphic forms of H, is nothing but image of this equivariant linear map. Okay, as Wittek discussed, the classical theory of theta correspondence provides a rather complete description of this global theta lift. Okay, and the main tool used in this analysis is the Siegel-Weyl formula and the Rannis inner product formula, which I will briefly, very quickly review now. Okay, to state the Siegel-Weyl formula, the two main players is the theta integral and the Eisenstein series. Okay, so associated to a Schwarz function phi, I can consider just the integral of this two-variable theta function over the one of the group. Okay, integrate over the entire group H. So I integrated away this group H, so I only get a function on G. Okay, so that's a theta integral Ig of phi. Okay, so it's a GA equivariant distribution given by this theta integral. On the other hand, I can also use the construction of the Eisenstein series, okay, to also produce such a equivariant distribution. Okay, so it's associated to a Schwarz function, have a standard Siegel-Weyl section of the degenerate principal series. Okay, again, constructed using the Weyl representation. Okay, given by this explicit formula. Okay, then you do the summation over the rational points of P quotient by G, okay, the Euro construction of Eisenstein series. Okay, so in particular, if it's specialized to this particular point S0, you know that you also get a GA equivalent distribution of the same form. Okay, so the special value of the Eisenstein series produce an analogous distribution. Okay, so Siegel-Weyl formula says these two distributions are actually the same. So if I assume the pair V and W satisfy the Bayes convergence condition, which nothing means the left-hand side, the theta integral is absolutely convergent. Okay, then this theta integral and the special value, the Eisenstein series, are in fact equal up to some explicit constant. Okay, and if the Bayes convergence condition is not satisfied, then we can still define the theta integral by a certain regularization process. And it was a long effort starting from the work of Coulter-Rallis to generalize the Siegel wave formula outside the convergent range, and also for all reductive Dedekind pairs of classical groups. Okay, so I would refer you to this nice article of Gancho and Takeda for the most general form of Siegel wave formula. Okay, but on the other extreme, I want to give you a really simple concrete example of Siegel wave formula. Okay, so let me just take the simplest example, take G and H to be the pair sp2 and O2. Okay, so I take V to be a quadratic space. Over the rationals given by the quadratic form x squared plus y squared. Okay, I'm going to take the simplest kind of Schwartz function, simply given by the characteristic function of the integral lattice Zp squared and finite places. And in infinite place, I take the Gaussian function, standard Gaussian function. Okay, so if you compute both sides, the theta integral is nothing but a classical theta series associated with this two-dimensional quadratic lattice. Okay, so that's nothing but theta series whose coefficients before q to the n is nothing but the representation number of writing the ways of writing n as a sum of two squares. Okay, and the right-hand side is a classical Eisenstein series of weight 1. Okay, and with this explicit character chi, this level 4 character, a quadratic character. And then compute the Q expansion of the Eisenstein series, you get explicit divisor sum given by summing over chi of d, where d runs over all the divisors in n. Okay, so now comparing the three coefficients, the Q expansion, you get explicit formula for the representation number. And I would encourage you to do this exercise. If you use the Siegel wave formula in the simplest example, it easily implies Fermat's theorem on writing a prime as sum of two squared. So an odd prime is a form of x squared plus y squared if and only if p is congruent to 1 modulo 4. Okay, that's really a conceptual proof of Fermat's theorem. In fact, people usually attribute to this the theorem to Fermat, but I think historians never find a complete proof in Fermat's work. Okay. Okay, now let me also remind you a little bit the Rallis inner product formula. Okay, and the key player is a doubling zeta integrals that was studied very detailed in the Wittek's lecture. Okay, so the key player is this doubling Hermitian space, W square, and the group G, doubling group G square, which is a quasi-split unit group in 4 variables, okay, the double size as G. Okay, so associated a pair of Schwartz function, I have a doubling Siegel-Eisenstein series, G square. Okay, and you can consider this double integral by integrating a pair of cusp forms against this doubling Siegel-Eisenstein series. And the idea is that it gives a very nice integral representation of the standard L function of pi. Okay, so let me remind you this global doubling zeta integral is factorizable if all the test data are factorizable. And for unramified data, you actually get a standard L factor, okay, then divided by certain explicit Hecke L factors. Okay, and when data are unramified. Okay, so I would define the normalized local doubling zeta integral by just doing this normalization. Okay, extracting these local L factors. So in particular, this normalized local doubling zeta integral will be 1 at all 5 unramified places. Okay, so in particular, it will be only non-trivial if there's certain ramification in presence. Okay, so using the doubling seesaw and the Ziegler wave formula for this pair V and W squared, we arrive at the Rayleigh's inner product formula relating the Petersen inner product of theta lifts and the special value of the standard L function. Okay, more precisely, this earlier theta lift I defined, I can do a Petersen inner product on the group H, and it will be equal to the special L value at this point S0 given by this formula, which also appeared in the Ziegler wave formula for the pair VW squared. Okay, and then multiplied by these local terms given by the normalized double integral. And as explained, this is in fact a finite product. Okay, any questions so far? So far, everything is reviewed. Okay, so now I want to highlight one special case, the case of equal rank. So I'm going to take M is equal to 2n. In other words, the two spaces I consider V and W have equal rank. So in this case, M is even integer, so I can choose the spin character chi to be just trivial to simplify things. And furthermore, the special point S0, by the formula on my previous slide, is in fact equal to 0. Okay, that's the special point that's most interesting. That's the center of the functional equation of the Eisenstein series, and also the central point for the special L value. Okay, so if you plug in Rayleigh's inner product formula, I actually get a criterion for the non-vanishing of the global theta lifting. Okay, so there is a global condition given by the non-vanishing of the L value, and also a local condition, namely this local zeta integral is not identical to 0. Okay, and in fact, these local conditions we understand fairly well. So the theta dichotomy tells you that in fact there exists a unique local Hermitian space of rank n over f over the local field, such that you consider corresponding local zeta integral for test function on that space is non-zero. Okay, and in fact, you can say a little more precise which Hermitian space. Okay, so tell you which space is non-zero, it's given by this recipe of epsilon dichotomy. Okay, so at a finite place, this local zeta integral is non-vanishing if and only if this sign condition is satisfied. Okay, so to pin down the local Hermitian space, there are two of them, so you just need to specify its Hasse invariant. It's either +1 or -1. Okay, so the Hasse invariant is exactly pinned down by requiring it's equal to some elementary factor given by the central character of pi evaluated at -1, that's a sign, and also a slightly less elementary factor given by the local doubly epsilon factor and its central value. Okay, so using this epsilon dichotomy, I actually have a complete recipe to tell you which space V I have to look at to make sure that all the local obstructions are removed. Okay. Okay, so the theta dichotomy associates to this automorphic representation pi a unique collection of local Hermitian spaces. Okay, such as the local theta double integral is non-vanishing. Or equivalently, I can just specify this collection of a Hermitian space at each place and package the information as just an adelic Hermitian space, which I will use the symbol bold V, okay, attached to this representation pi, or rank n over the ring of Adel, so there. Okay, so now there are two cases. So this adelic Hermitian space could actually come from a base change of a global Hermitian space over the number field F. Okay, so in this case, if it actually comes from base change, I would say this Hermitian space is coherent. Otherwise, I would say it's incoherent because it doesn't really come from a global space. Okay, it's just some kind of incoherent collection of local data. Okay, so I associate to this adelic space, I'm going to define a sign simply given by the product of local Hasse invariant. So the Hasse principle implies that it's both this adelic space is coherent if and only the product of local Hasse invariant is +1, and incoherent otherwise if the epsilon about V is -1. Okay, and if you take the local epsilon dichotomy and multiply it together, then I actually have equality of signs. Okay, so the product of Hasse invariant of this adelic Hermitian space is in fact just given by the central value of the doubling z epsilon factor of pi. Okay, so now I have two cases, depending on whether the sign is +1 or -1. Okay, so if the sign is +1, then this both V is coherent. In other words, it comes from phase change. And from the discussion on the previous slide, I actually get a criterion of the non-vanishing of the global theta lift associated to this particular space in terms of a very nice criterion, right? Just in terms of the non-vanishing W standard L function. And what about other global Hermitian spaces are not given by V? Well, the global theta lift will vanish, okay, simply because of local reasons. Okay, if the sign is -1, then this both V is incoherent, then the global theta lift is only 0. Okay, you don't even need to look at the L function. Okay, simply because local reason the global theta lift will vanish. Okay, so in some sense, it's not very interesting to look at the theta lift when the sign is -1. Okay, so in the coherent case, right, there's no global theta lift attached to this incoherent space, and because of sign reason, the central value of the L function always vanish. Okay, so it doesn't give you too much information. Okay, but if the sign and functional equation is -1, it's very natural and very interesting to study the central derivative. Okay, simply because there's an extra symmetry at the central point. Okay, so the Birch-Swinton-Dyer conjecture and its generalization by Balius and Bloch for higher dimensional varieties predicts there should be a link between the non-vanishing of the derivative with non-triviality of certain algebraic cycles on certain varieties. Okay, so at least you can hope such a link is predicted by this deep conjecture as long as this pi is related to the L function of certain varieties. Okay. Okay, so now the idea is in the second case, we'd like to develop a parallel story, okay, analogous to the classical theta lifting. Okay, and in particular, I'm going to define a variety and its algebraic cycles. Okay, I'm going to start with a certain incoherent space, both V, and associate to a unitary Shimura variety. Okay, I'm going to define an arithmetic analog of the theta function using its special cycles. Okay, using this arithmetic version of the theta function, I will be able to define arithmetic version of the theta lift. Okay, so now the theta lift will no longer be the space of automorphic forms, okay, but rather is a subspace of the Chow group, okay, of algebraic cycles of codimension n, okay, modular rational equivalence on this unitary Shimura variety. Okay, so analogous to the classical theta correspondence, which in my terminology is a coherent case, giving a criteria of the non-vanishing of the global theta lift in terms of central L value, the Culas program on arithmetic theta lift aims to establish a similar criterion, okay, for the non-vanishing of the arithmetic theta lift, but now in terms of a derivative, okay, because that's the natural thing to look at when the sign is -1. Okay, so in order to achieve this goal, okay, similarly, we're going to need several ingredients parallel to the classical story. First of all, I need to know that this arithmetic version of the theta function is modular. Okay, it's an automorphic function. Okay, and I would also like to have these two key ingredients in the classical theory. Namely, I would need to have a arithmetic version of the Ziegler wave formula and the Rayleigh's inner product formula. Okay, and in fact, these ingredients were conjectured by Kudla in the 90s. And in fact, these conjectures were largely settled for quaternion ionic Shimura curves over Q, accumulating in the monograph of Kudla, Rappaport, and Young. Okay, they in fact established these conjectures in this Shimura curve case. Okay, so back in the 90s, these general conjectures for Shimura varieties of a higher dimension were seemingly far from within reach at the time. Okay, but recent years has really witnessed very exciting advances on all these conjectures, even in the most generality in higher dimension. Okay, so the goal of my lecture will eventually to survey some of these recent events. Okay, so that's a summary of what's going to happen. Any questions so far?
Does it just look in the unitary setting or on the ST and O setting as the story is complete too?
Of course, there are conjectures, but we know a little bit less in that case. Yeah, but for the purpose of this lecture, I'm going to focus on unitary group where the results are more complete. Okay, any other questions? Okay, so that's what I'm setting to, right? So I'm going to define the unitary Shimura variety, arithmetic theta function, and use to define a version of arithmetic theta lift. But in fact, in doing that, I'm going to give you an interlude. So I'm not going to jump directly from classical theta correspondence to arithmetic theta correspondence. In between, I'm going to introduce the third story, okay, the geometric version of the theta lift, okay, to just give you a more sense of analogy. Okay, so let's introduce a unitary Shimura varieties. Okay, so in fact, I'm going to give you two perspectives. One coherent perspective, that's people thinking about Shimura varieties traditionally think about them. Okay, I'm going to start with a CM extension of to the real number field. Okay, as before, V is a Hermitian space and H is its unitary group. Okay, so I'm going to fix a complex embedding of this CM number field, and I assume a particular signature condition. Okay, I call V is standard indefinite if V has signature m-1, at the real place I fixed, and positive definite m0 signature at all other real places. Okay, so associated to this standard indefinite Hermitian space, I have a system of unitary Shimura varieties indexed by all the neat open compact subgroups K on the finite idealic points of H. Okay, so each of the variety, a Shimura variety, is a smooth quasi-projective variety of dimension m-1. Okay, because of my signature condition m-1, 1. Okay, and it's projective if the Hermitian space is anisotropic. Okay, this is the case if the total real number field is bigger than Q. Okay, so its complex points have this complex uniformization, okay, given by this double quotient, where the associated Hermitian symmetric domain is actually quite classical one. Okay, so it's the moduli of negative complex lines in this complex Hermitian space. Okay, and it's isomorphic abstractly to the complex open bore of dimension m-1. Okay, so why do I choose this particular signature condition? Okay, I think this was discussed in Sophie's lecture before, right? So by the long-length philosophy, the motive VL function of these Shimura varieties should be factorized into a product of automorph VL functions. Okay, and this particular choice of signature at infinite places means that the L function appearing there ought to be the standard L function. Okay, so if you pick arbitrary, more complicated sign combination, signature combination, will get more complicated L function involving exterior power L function or automorphic representation. Okay, so the standard L function appears that suggests our terminology and also explain the relevance to our program because the crucial player, the doubling method, it gives us access to the doubling L function, standard L function. Okay, and another important remark is that these kind of Shimura variety are actually of abelian type, so it's not of PL type. Not like the unitary Shimura variety associated to unitary similitude group. So it's actually technically more complicated to work out its Étale cohomology and L functions. Okay, but it's now done, or will be done in the forthcoming work of Kissen, Xing, and Zhu, under the help of endoscopic classification for unitary groups. Okay, so it's kind of satisfying that we actually understand the motivic L function to some degree of these unitary Shimura varieties. Okay, now I give you a second perspective on this unitary Shimura variety. So instead of starting with a global Hermitian space, I'm going to start with an incoherent Hermitian space. Recall that means it does not come from a global Hermitian space, and the product with Hasse invariance, local Hasse invariance, is -1. Okay, but if I assume this Bode-V is totally definite, I assume its signature at all Archimedean places is definite, then I can play the following game. Namely, if I pick an arbitrary embedding, complex embedding of F into C, I can use that particular infinite place and switch the signature from positive definite M0 to M-1, 1 at that particular place, while don't do any changes at the remaining places. The net effect of this change of signature at one particular place allows you to change from this incoherent space to a coherent space by just changing one of the Hasse invariants. Okay, and in fact, I can do this for arbitrary embedding. I don't need to fix out any embedding. Okay, the theory of a conjugation of a Shimura variety tells you the different Shimura variety obtained by choosing different embeddings actually can be intrinsically defined over the number field, over the reflex field F, okay, without being viewed as a subfield of C. Okay, so it's abstractly defined over F. Okay, therefore, this perspective has the advantage that the totally definite incoherent Hermitian space actually gives you a system of unitary Shimura varieties that is canonically defined over F. Okay, without the need to choose an embedding. Okay, so now comparing our previous discussion of theta lift, we also have a dichotomy perspective on unitary Shimura varieties, depending if you choose this coherent perspective or incoherent perspective. Okay, so if you want to study the geometric invariance of the Shimura variety, in other words, you are looking at the complex manifold associated to this Shimura variety X, okay, over the algebraically closed field C. That means you have to choose a particular embedding of F into C, okay? So that choice has to be involved. Okay, so in this case, the coherent space associated with V should play a canonical role. Okay, and by our earlier dichotomy perspective, what you ought to see is when you study geometric invariance, some kind of special values of analytic quantity ought to appear. If you want to study arithmetic invariance, namely those invariants really live over the number field F, then you shouldn't make any choice of the embedding. Okay, so the data should be chosen at the incoherent space, and that's a perspective you should take. And on the analytic side, the special derivative should appear. Okay, and then we want to relate these arithmetic invariants to derivatives. Okay, any questions so far about this dichotomy? Okay, and that's what I'm going to do. I'm going to study first the geometric invariance of the complex Shimura variety, and then see what happens later, the arithmetic invariance. Okay, now that achieves our first goal. I have defined for you an ambient variety, the unitary Shimura variety. Now I need to define for you the cycles on it and use it to form a arithmetic version of the theta function. Okay, so let me tell you what these special cycles are. Okay, so now let me fix these initial data. So V is standard indefinite Hermitian space, or equivalently, you could take associated totally definite incoherent space. Okay, so they only differ at one Archimedean place. So if I take the finite adelic points, they are the same. Okay, I'm going to use Bode F to denote the common finite adelic points. So both of them. Okay, so if I start with a vector in a coherent space with totally positive norm, then its orthogonal complement is also a standard indefinite Hermitian space, but with rank 1 less. Okay, so I can run the same construction to get a Shimura variety of dimension 1 less. Okay, in other words, on this unitary Shimura variety, I have a huge supply of Shimura subvarieties of codimension 1. Okay, so that's a divider. I will define a special divider associated to this vector y to be given by just this sub-Shimura variety associated to the subgroup. Well, generally, you don't have to start with a rational vector. You can start with a finite adelic vector as long as the norm is a global, totally positive element. Okay, in this case, you can find a rational vector and a group element, H, such that y is a translator of x. Okay, so in this case, I would just define the special divider associated to x to be a Heck translator of the subvariety, okay, by this group element H. Okay, so that's the case of codimension 1. Of course, there's nothing stopping me to do not just one vector, but the tuple vectors. So if I take an arbitrary integer that is smaller than the dimension of x, okay, and I take a tuple vectors, n tuple vectors, such that the moment matrix is totally positive definite, then I can define the special cycle now of codimension n, okay, simply by taking the fiber product of these dividers. Okay, so I'm taking the intersection of n dividers, and I should get a codimension n cycle. Okay, and one observation you can make is that when I do this construction, the cycle really only depends on the rational span of the vectors inside the finite adelic points. Okay, and to emphasize that dependency, I would just write the special cycle to be depending on this f rational span of x. Okay, so I can make this construction exactly because this totally positive definite assumption. Okay, so whenever I throw in a vector into it, when you do this orthogonal complement construction, you get the correct codimension. Okay, so that's why I said it's a case of proper intersection. Okay, but what if I take a tuple whose moment matrix is still semi-definite but singular? Okay, there's some linear dependency on these vectors. The intersection of these special dividers will in general be improper. Okay, it has a wrong codimension. So in order to define the correct codimension cycles, you better make some modification. Okay, so in this case, we use some intersection theory. So let me take L to be the tautological line bundle on the Shimura variety, okay, which is simply formed by this double quotient, where L is a tautological line bundle on this complex open ball. Okay, so if I take, in the simple case, just take a rational vector whose norm is totally positive, then the excess intersection formula implies if I take a self-intersection, okay, of the same divisor, I actually can compute it in terms of taking the intersection of the divisor itself with the first Chern class of the dual of the tautological line model. Okay, so that's a consequence of computing self-intersection. Okay, so if you look at this formula, it would suggest, in general, if you have an improper intersection, I would first take the genuine span of this twofold vectors and look at the corresponding cycle. Okay, that I may have the wrong codimension, but I can make it correct by pairing with the first Chern class of L dual to the correct codimension. Okay, so I do a little padding to make it into the right child group. Okay, so that gives you deal with the improper intersection. Okay, so now I can consider weighted subspecial cycle for any Schwarz function and any semi-positive definite Hermitian matrix. Okay, I can take a linear combination of these special cycles by averaging with the values of the Schwarz functions. Okay, so these special cycles you can think of as some kind of cycles with a fixed moment matrix, the T form. Okay, whatever they are, they should be thought of as the kind of analog of representation numbers of quadratic forms. Okay, so now I can introduce a arithmetic version of the theta function. Okay, so define the arithmetic theta function. It's now a generating function. Okay, using these special cycles indexed by the moment matrix T, and then multiply Q to the T. Okay, where this formally looks like a Q expansion of a Hermitian modular form. Okay, so this is a formal generating series valued in child group. Okay, and this variable is lying in the Hermitian upper space, okay, of genus N, and Q to the T is this product exponential function. Okay, so if you want it more identically, I can also write it more complicated using the action of the Weil representation to make it more like the identic formulation of theta function in the classical setting. Okay, so I'm going to use, so if I have a more general identic variable g, I'm going to use the Weil representation to act on the Schwarz function and look at the corresponding special cycle, and then multiply the corresponding Archimedean factor also using the action of the Weil representation. Here, the phi infinity is a standard Gaussian function. And in particular, you can evaluate the moment matrix because the Gaussian function actually factors through the moment matrix. Okay, so what it is nothing but the formal free expansion of this sum, okay, of the Weil representation acting on this Schwarz function, and we multiply these cycles. Okay, so if I write this way, it formally just resembles the classical theta function. Okay. And moreover, when I do this definition, it's actually compatible when I vary the system of open compact subgroups, and in fact defines a formal sum, okay, where I just suppress the subscript k. Okay, now it's a formal generating series valued in the limit of the child groups of the system of Shimura ranks. Okay, so any questions about the definition? Okay, so now the first result, and actually was the origin of the entire theory, okay, is that there's certain modularity to this generating series. Okay, I'm going to tell you the geometric story first by extracting a geometric invariant of these cycles. What I do, I simply take its Bethe cohomology class, okay, of the associated complex manifold. So in particular, by taking the Banach homology class, this generating series actually give you a generating series not in child group, but in the cohomology group, okay, whose coefficients actually encodes information about the geometric intersection numbers of these special cycles. It turns out these intersection numbers with various special cycles have many hidden symmetry and relations as encoded by the following modularity theorem. Okay, so this theorem of Coulomb-Nielsen, saying that the formal generating series given by the cohomology class of this arithmetic theta function actually defines a modular form. Okay, so this is a certain space of holomorphic Hermitian modular form of a given weight and character. Okay, but now not valued in C, but valued in the cohomology. Okay, and in fact, Coulomb-Nielsen theory is in much more general setting. They define the generating series of special cohomology classes for more general locally symmetric spaces. Okay, you don't even need to have a Shimura writing. Okay, but it's a saying, okay, these different special cycles really have the hidden symmetry between them. So how do they prove this geometric modularity theorem? Well, how do you prove the modularity of the Euro theta function? Well, you use the Poisson summation formula. And in fact, they also use Poisson summation. Okay, so let me give you a glimpse of the proof ingredient. Okay, so in fact, they produce another theta function, not as a pure function, but as a theta function valued in differential forms. Okay, so the proof relies on the Coulomb-Nielsen-Schwarz form, okay, which is a Schwarz function valued in the space of smooth n forms, okay, on the Hermitian symmetric domain. Okay, it's invariant on the real points of H at that particular real place, and importantly, it's a closed form if you evaluate at any point, okay, of this Archimedean Hermitian space. Okay, so this is happening only at this particular real place I picked, but you can complete it at all other places by just inserting a Gaussian function, and also complete it at finite places, okay, using my test function at finite places to get a Coulomb-Nielsen theta function. Okay, but now it's a function gives a closed n form on a complex Shimura variety for any particular choice of G. Okay, what they showed, which is non-trivial, is that this differential form valued theta function actually represents the holomorphic generating series given by the cohomology class. Okay, but the advantage is now you have this Coulomb-Nielsen theta function. You can use Poisson summation to show it's actually automorphic form. Okay, in fact, in this case, it's a non-holomorphic automorphic form. But after passing from the closed n forms to the cohomology class, it actually kills all the non-holomorphic terms. I mean, all the non-holomorphic terms become exact forms. Okay, and miraculously recover the generating series given by the cohomology class of special cycles. Okay, so now here, yeah.
So you had the place V naught, and then you had the other Archimedean places.
Yeah.
So you're saying that at the other places you can choose arbitrary Schwarz function at the other Archimedean place.
No, I'm just choosing.
Oh, you're choosing Gaussian.
Gaussian, yeah, because at all other places the Hermitian space is definite.
But at V naught it's a different choice that you didn't tell us about.
V naught is the fixed embedding I chose.
But the choice is also very particular, right? So
Yeah.
the Coulomb-Nielsen choice is very particular.
Yeah, so if you want to look at the complex points, you have to choose a complex. That's the one you use. Good. Any other questions? Okay, so here's a summary of what has happened. So we have reviewed a bit the classical theory of theta correspondence. Okay, so the key player is two-variable theta function. Okay, and the two ingredients, the two important formulas, the Siegel wave formula and Rayleigh's inner product formula. So I have achieved in the geometric setting and arithmetic setting a theta function as well. Okay, so in the arithmetic setting, I have defined for you a generating series of special cycles, but now valuing the child groups of the Shimura-Rayleigh. And I also defined for you a geometric version, which is kind of between these two. Okay, it's given by the geometric invariance, the cohomology class of the special cycles. So naturally, you wonder, what are the analogs of the remaining blanks, right, in the geometric setting and the arithmetic setting? So what are these things? Okay, so I'm going to tell you, right, the analogous version, geometric version of the Siegel wave formula and Rayleigh's inner product formula. Okay, so now the geometric modularity gives us a distribution, okay, now not valued in the product of automorphic functions on the product G and H, but now on the automorphic forms of G, and you replace the automorphic form space by the cohomology space of the Shimura-Rayleigh H. Okay, again, it enjoys very natural equivariance properties, okay, but only for the finite eidetic points. Okay, so using it, I can lift automorphic forms to cohomology class on the Shimura-Rayleigh, and the complete analogous, I can take the Petersen inner product on the group G. Okay, now instead of getting an automorphic form on H, I get a cohomology class on the Shimura-Rayleigh. Okay, so this is called a geometric theta lift or Kudla-Musen lift. Okay, this formation is compatible when I vary the level K. So I actually get a well-defined class in the limit of the cohomology groups. And complete analogously, I can define the geometric theta lift. So let me pick an automorphic representation pi, and let me assume it has a particular weight and a character. Okay, so now I can use all the choice of Schwartz functions and all the vectors with a particular weighted character, okay, and form the Kudla-Musen lift to get a geometric theta lift. Okay, so now it's not a subspace of automorphic forms, but now a subspace of cohomology of X. Okay, so using this, now I can tell you the analog of the Siegel wave formula and Rayleigh's inner product formula should be. Okay, so the zero Siegel wave formula is relating the theta integral with a special value of Eisenstein series. So what is the analog of the theta integral in this case? Well, I need to produce a number from the geometric invariance. Okay, so I can take, for simplicity, assume X is projective, and can take the degree map from the top cohomology of the Shimura-Rayleigh to the complex numbers. Okay, so that's a numerical invariance attached to these special cycles by just taking, okay, your cycle of certain dimension and the pairing with the first Chern class of a tautological bundle. Okay, so I hit this top codimension cohomology group. Okay, and I apply a degree map to get a number. Okay, so started from a topological cohomology class, I get a number, and this is really referred to as a volume, geometric volume. For example, if you just take Z to be XX, X, the fundamental class of X itself, is nothing but recovering the geometric volume of the Shimura-Rayleigh itself. Okay, so if I wanted to behave well under varying K, I can normalize this geometric volume by quotient on the volume of the Shimura-Rayleigh. Then it becomes independent of the choice of K. Okay, so now that's my numeric invariance. It should be thought of as analog of the theta integral. Okay, it in particular now produce from a Schwartz function to an automorphic form on G, just as the Eisenstein series. Okay, so the geometric Siegel wave formula, as proved by Kudela, says that if you take the special point s equal to m minus n/2, then the volume of the generating series of geometric theta function is nothing but the special value of the Eisenstein series. Okay, and of course there's a particular choice of the test function at Archimedean place I haven't told you. Okay, but whatever it is, it should be a Schwarz function on this coherent space. Okay, on the identical points of the coherent space. And in fact, it can be constructed from the Coulomb-Nielsen-Schwarz form. Okay, and finally, what about the geometric analog of the inner product formula? So I need to define for you an inner product now on cohomology instead of automorphic form. Okay, what do? So if I have a cohomology class and another cohomology class, I can take the cup product, again, cohomology in higher codimension, and apply the normalized volume to again extract the number. Okay, so that gives a well-defined inner product, okay, extracting geometry invariance from this cohomology class. Okay, so again, it will be compatible when varying k, and I'm going to denote this geometric inner product, okay, to emphasize it's really depending on this complex manifold. Okay, and combining the geometric Siegel wave formula and the Rayleigh's inner product formula, I have the geometric inner product formula saying that the geometric theta lift, its inner product, is in fact expressible as the same in the Rayleigh's inner product formula, the special value of the L function, and multiply a bunch of local doubling zeta integrals. In the special case, if you just take 2n to be n minus 1, right? So of cohomology class, in fact, is given by middle dimensional cycle. Okay, so we are not really padding with any tautological line model. So we're just pairing these middle dimensional cycles, and that's nothing but the geometry intersection numbers of these special cycles, geometric theta lift. And it gives you a relation with a near central value of the standard L function. Okay, let me mention that this theory of geometric theta correspondence have many applications to study the cohomology of Shimura-Whitey and more general locally symmetric spaces. And for example, Bergeron, Milson, and Lang have used these special cycles and the geometric theta lift to prove cases of a Hodge conjecture, and also the Tate conjecture for these integer Shimura-Whiteys, at least when the codimension is very small or very big. Okay, that's one important application of this theory. Okay, so let me end with a summary. So I have completed the second row of this diagram by telling you the geometric version of the Siegel wave formula and Rayleigh's inner product formula. And you can see the analytic quantity on both sides are the same, essentially same. And in fact, the proof of this formula is by realizing this geometric volume and geometric inner product formula, geometric inner product, okay, as a special cases of theta integral and Rayleigh's inner product. Okay, so it's really a geometric realization of the first row. However, the third row is a completely different beast. Okay, and I will leave this as a question mark, and I will discuss arithmetic theory next time. Okay, thanks for your attention.
Are there any questions for now?
Can I?
Yes. Please.
Well, I don't know if maybe we can leave it to the Q&A session, but could you comment on these applications to the Hodge and Tate conjectures, like how this works?
Well, so the geometry.
Maybe briefly, but maybe it's a long story.
It's a very long story. Yeah, but to just oversimplify it, so this geometric theta correspondence will give you a certain map from space of automorphic forms to a subspace of a cohomology class, subspace of cohomology of these Shimura-Whitey. And what they did is use these. Of course, when you do this lift, it could be 0, right? But this Rayleigh signal product formula, etc., these tools tell you that this lift, in fact, in many cases are non-zero, and sometimes even give you a bijection between these automorphic form space and the cohomology space. And what they are able to prove, for example, in the Hodge conjecture case, all the Hodge cycles are actually spanned by special cycles. Of course, that's a drastic simplification. Okay, but ideally, that's what you eventually prove. Okay, so of course, it's not all special cycles, but special cycles part something you understand. So you span all the Hodge kind.
Okay, so Charles, in the context of the second row, right? So could you go the other way, meaning you start from a cohomology class, and then you leave to produce automorphic forms on G? And has anyone used this direction to produce anything?
Not as far as, no. I sometimes wonder this too.
Could you repeat the question?
So the question is, you can see in the classical theta correspondence, you can go from G to H and H to G in both ways. So far, I have described one direction, namely lift automorphic forms from G to cohomology class for Shimura variety associated to H. So the question is, can you go backwards, start from cohomology class on the Shimura variety and produce automorphic forms? And the answer is, I don't know such an instance, and I sometimes wonder myself.
But in some sense, this Hodge conjecture is kind of doing that, as you explained. Like you're kind of generating cohomology Hodge classes.
Well,
I don't know. Maybe
you're right. Well, in the case it's actually bijection, of course, you can go backwards.
So maybe let's take a 5-minute break and then start the regular Q&A session. And let's thank Charles.